Hello and welcome to Drawn Out Conversations, where I get the opportunity to talk to engineering leaders about their architecture and how they've chosen to build things to scale their teams and their business. I'm Rob Zuber, CTO of CircleCI, and today I'm joined by Zachary Crockett, founder and CTO of Particle. Thanks for joining me today.
My pleasure. Great to see you.
Just to get things started, can you give me a super brief overview of what it is that Particle does and then how you go about doing it from an overall system perspective?
Sure. So Particle is a connectivity and distributed computing platform for IoT devices. We provide a full stack solution that includes embedded hardware, embedded software, networking connectivity, device management, and APIs for engineers to interact with IoT devices remotely. So at a high level,
Cool.
That's what we do.
And so what does that look like in terms of the pieces that you've built and how they all fit together?
Company colors are cyan, so I'll go with this.
That's a good start.
Most companies like us, SaaS companies, have, let's say, okay, here is the cloud.
And that shape.
Down here among us mortals, we have things like mobile phones and computers drawn absolutely to scale that talk to a REST API, right? Mm-hmm. So that's super common for any SaaS company.
Yep.
We have one too. However, that's only half the story, because a lot of what Particle does is provide an easy interface to IoT devices. And IoT devices generally are run by microcontrollers, not microprocessors. Okay. They have tiny amounts of compute, and all the protocols that are typical here are a great big waste of resources on that side. So we have a thing that we call the device service, which is the main unique differentiating thing that is different about Particle than about most others. It does similar jobs to how an external device talks to the Particle cloud as a REST API, but this is for little things that maybe look like this. And it allows for bidirectional communication, which is not true for everyone. Maybe I should just actually use one of these things up here.
Like it. That's actually a really good representation, all things considered. So
drawn it a few times.
So just to help kind of connect my imagination around it, I would guess that it doesn't look like this when there's one of these in my home. There's probably some specific purpose that it's being used for. Maybe it's not even in my home, in a factory or whatever.
Right. So this is a dev kit. It's a development kit. Mm-hmm. And when one is prototyping an IoT solution, one buys one of these from our website, gets it home, goes through setup, gets it connected to the cloud. It could be over Wi-Fi or cellular or over a mesh network, and starts prototyping using our ecosystem of tools. When one goes to scale, there is a different set of hardware that we sell, SOMs, S-O-M, system on a module, which is for mass production. So you would, instead of buying one of these or a handful of these, you'd buy a tray of 50 SOMs, which you then, in your own manufacturing plant, solder onto your own board.
Onto a device that has some peripherals.
Exactly. Yeah.
And I'm imagining this is designed to drop into a breadboard or something, so you can connect all those things.
Exactly. There's one over here somewhere.
I don't carry any of these things around with me, by the way.
Yeah.
This is awesome. It's so exciting to me.
Unique to my job. So.
Yeah, very cool. So you mentioned limited resources and the constraints of the environment that you're operating in. And as I understand it, you, as Particle, wrote your own operating system to support that type of environment. Is that correct?
Yeah, sure.
So we at CircleCI, we tell people never to do anything that someone else could do for you. This feels like the exact opposite. So I'm curious, how it is that you end up in that place where you need to build an operating system. And then I'm really excited to learn a little bit about this operating system.
So let's talk about what runs on this actual device. The software that runs on that device we call our device OS. Okay. And it is open source. You can find it on GitHub, Octocat.
Very nice.
And that was a decision that we made very early on. Mm-hmm. So the device OS, I completely agree with you that whenever possible, you should avoid reinventing the wheel and avoid creating things that that you can buy or use instead. Our device OS contains a lot of things. Let me list just a few, and many of them are using open source libraries that are already out there. Okay. And widely used. One of the key components that we have is something called FreeRTOS. So when you talk about operating systems on these little devices, they are not an operating system in the same sense as the ones that run on our laptops. They're called RTOS, real-time operating systems, because the constraints on time are really tight. You have to make sure that motor gets a signal this frequently. You have to make sure these voltages stay the same. You have to make sure this component gets triggered at that point, that the sensor gets read, that often. Right. So you have hard constraints on the timing. FreeRTOS is a massive and super valuable component there. We primarily use the threading and sort of mutex functionality there, which is appropriate for these kinds of devices. On top of that, we have a lot of platform specific, I'll just call it platforms here, which might be, it's code that is specific to certain hardware. So we support a bunch of different hardware. We first released back in the day something we called the core, the Spark core. I mean, all these devices sort of look roughly the same, little circuit board with a module on it and some pins. That was back in 2013 that we shipped that. It's an ST microcontroller, and it had a TI Wi-Fi module. So this is Wi-Fi. In 2014, we released the Photon, which looks just the same. And that's also Wi-Fi. And that was still, it was a slightly different, but still an STM32. So these are all 32-bit microcontrollers. But it had a Broadcom module.
And is this mostly increases in speed and performance based on what's available, or what drives new releases?
Yeah, the selection of these underlying components, like what's your microcontroller that you're going to reprogram and what's the connectivity radio you're going to choose, is driven by market forces. It's driven by supply chain, what things are widely available, because we want it to help companies go to scale. And so these components have to be very widely available. This TI module, for instance, was essentially end-of-lifed pretty quickly. But we built traction with the core that allowed us to get conversations with Broadcom, who before that point wouldn't talk to people like us.
I got it.
Right. I'm not exactly sure when now, but 2015, 2016, we went into, we released a thing we call the Electron, which was cellular. We got into cellular for the first time. We ran a Kickstarter campaign for that, was very successful, used the same ST microcontroller as the Photon, and then a U-Blocks module, which is a company that makes modules that can connect to different cell towers. This is 2G and 3G.
Out of curiosity, what sort of use case drove you to cellular versus Wi-Fi?
Oh my gosh. People were doing they loved our ecosystem of tools. If I think of like, to program one of these things, and this sort of gets back to the question you asked earlier, how do people get into this, dealing with the tiny devices? One of the other services we have, which is essentially a front-end interface to the REST API, is our web IDE.
Okay.
And this is, it's a web page. You can go to build.particle.io, and you have, toolbar on the left, some tabs across the top, and then, code indented like we do. And so there's a bunch of tools there. And you go to this web page, and you write code there, and you just hit a flash button, so it looks like a lightning bolt.
Yep.
And we handle compiling that code into a binary appropriate for whichever device you have chosen that you want to send it to, which they're all different platforms, which gets back to what I was talking about there. Compiling it, and then sending it through the cloud, managing a secure and reliable over-the-air firmware update for these devices.
Wow.
And part of the code that we have to write in the device OS is, I'll just go ahead and say here, this is pretty high level actually, so I'll put it up here, is OTA, over-the-air update functionality.
Right.
We make this, it's all encrypted, all secure. Every device has unique asymmetric keys. New sessions, same encryption you use with your bank and whatever, anything like that, but appropriate for these devices. It's secure, it's reliable. The devices can, safe recovery. They'll if anything goes wrong, they go into something called safe mode.
So tell me how that works. This whole I'm upgrading this device. It's a tiny little device. I've got a new version compiled in the cloud that's going to be pushed down over the air, over this, and it's all constrained, and it's not going to end up half updated and broken.
Right.
Bricked, I think is the technical term.
Exactly.
Right?
Yeah.
So how does that happen? How is the device structured in a way that allows that to happen?
Yeah. So the curious can go to github.com/particleiot/deviceOS, and it's all there. That repo is enormous. We used to get a bunch of open source contributions, and beyond 2014, 2015, the repo got big enough and complex enough that has slowed to a crawl, though, the team that works in there all day, every day, their work is always publicly visible. But that's where we get a lot of the community engagement. So how does that work? There is, obviously we have to compile it somehow. So, there is. We have a thing that's a compile service. So you send certain API requests, and it's like, go build this thing. And it's like, okay, cool, built a thing. You hand it source code, and a binary comes back.
As someone who does a lot of compute in the cloud, is this cross-compiled, or do you have a giant pile of ARM? Oh, okay.
It is cross-compiled because for anybody who doesn't know what that means, when I write code on my machine, I write a Ruby script or a C, let's call it a C program on my machine, and I compile it for my machine. The compiler is a program that can run on my machine just like the binary that was output by the compiler. When you have to run a compiler on one machine that will output something that can't run on that machine, that in fact has to run on a different architecture, you call that cross-compiling, and it is a pain. So a lot of embedded engineers, they start at a new job and they spend the first month just trying to get their machine set up, so that it will work smoothly in their workflow to get code cross-compiled.
So I'm assuming you have a giant pool of Linux machines, x86 sort of thing, but then you're using that to create the output and then send it down to the devices.
Yeah, exactly. And so in the device service and some other intermediate services, you take that binary, You chunk it up, you create checksums for each chunk, and send it down to the device. So, well, let's see. Yeah. So chunk. Each time you send one down, the device is checking checksum, storing it in a certain place in the spare flash that you've got reserved for this job. When you've got it all saved there, say there's some flash in here and it saves all the chunks. Maybe it misses some, saves some more, misses some, saves some more, because these devices are talking over UDP, and dropped packets are a real thing. Invisible to us humans most of the time, but happens a lot. When it gets through an iteration, part of what the device OS OTA functionality does is say like, okay, hey, at the end of that, I am missing chunks 372, 528, 529, and whatever. It gives a list of the ones it missed. And the device service will send those down. And you keep going until everything is saved in Flash. So device does a full checksum, says it all checked out, and reboots.
So that's the current version of the operating system effectively has the code to evaluate that the new version is going to be safe because it has all the pieces?
So...
or within this OTA module, I guess, rather than the operating system itself.
How about, at a very high level, what's on the device is we've got this will be a few boxes instead of a ton of boxes. We have a bootloader. We have, let's say, one or more system modules. It depends on the particular architecture. Let's say there are two in this hypothetical one. So we've got a couple of system modules. Then you have the user or product application. So the code that you end up writing as a user of Particle in the Web IDE is only this user application.
Okay.
So this compiles down to a very small binary.
I see.
Which is
great point.
reserved. There is part of the flash memory reserved just for this application. And so we send it down, say there's a gap up here for sending down OTA. So when the OTA starts, user application keeps on running. There are different modes. Sometimes it keeps running, sometimes it doesn't. But this keeps running, just doing its thing, completely unaware that an OTA is happening. There is a system event you can get to get a heads up that an OTA is happening.
This is more like analogous to a deploy than to, I was thinking in terms of upgrading the whole operating system and all the risk that goes with that. But this is effectively, I would think of this in a container sort of world where you're just saying, to your point, the hook, like you're going to be shut down. Is there anything you want to do? Now I'm going to replace you with the new version of the binary. Okay.
Yes, with caveats, because you can build a user application for a new version of our device OS. We've released the device OS something like 3 or 4 times already in 2019. I've lost track, but we release regularly. And anytime you build a user application, you choose which version of the device OS, which is, this chunk is what we call the device OS. And so if you build against a new version, then you'll do the OTA to send this, your context switching back and forth between running the user application and then taking care of system tasks. Running the user application, taking care of system tasks. One of these is saving all those chunks from the OTA into this spot. When it's all done, we say, bye-bye, signal, we're shutting down, and the whole thing reboots. When the bootloader sees that, there is a flag set up here that, hey, we have an update saved, it will, again, verify some checksums, and then copy this into that space. And this code is like, rock solid, like barely changes. You do not make anything dangerous happen here. You're not online yet. You don't, leaving out huge parts of the system. Once that is finished, then we boot up into the system.
Got it. So this all started because I was interested in the mobile use case and how, what drove, I think we were only 3 systems in, but what drove that transition from Wi-Fi to then extending out the platform into getting on the mobile network? I mean, I can think of some, but I'm just curious what people are doing with this platform.
Totally. The one caveat, to go back to something you said, you're like, oh, but you're not updating this. Yeah. If you build the user application for a new version of the device OS, there is a dependency chain where this sort of has some metadata that says, I depend on device OS, version 52 or whatever, and what you have here is 51. And so the system will see that, boot into safe mode, not run this application because it assumes like the dependencies aren't met. And the device service will start sending down automatically that new version through the same process. It'll send down, say, system 1, and then reboot. Copy that in. It'll send down system 2, reboot. Once the whole dependency chain is met, then it boots into the user application.
Okay, before we get back to the mobile thing, how long does a reboot take?
Oh, a reboot is basically instantaneous.
That's what I would have thought.
Yeah, because these
I'm
things...
used to so many things getting loaded up, but
it's like
I just...
30 seconds, a minute, 5 minutes,
yeah, exactly.
I mean, it's milliseconds, or depending on where you say, like, it's done, microseconds to milliseconds, it's very, very fast.
That's awesome.
Yeah.
I'm going to use one of those as my laptop.
Yeah.
Okay. So mobile, getting into the mobile network.
Okay,
what drove you there?
So let's see, you were asking, we were making Wi-Fi things, and what were people trying to do that made us say, oh, perhaps we should try to become a cell carrier. Right. That seems like a crazy thing to do.
Yeah.
I remember people, there was a rancher, this story particularly I was like, what are you doing? Where he was playing with the Photon. He loved it. He was prototyping some things. He wanted to use Wi-Fi Direct and turn every single one of these things into a hotspot that could all talk to each other. And he wanted to essentially create, he was wondering whether it was possible to create a mesh network out of Wi-Fi devices and cover his entire ranch, or at least the entire fence. So he could tell when cattle were bumping up against the fence, or if the fence was coming down, had any gaps in it. So there's this huge area that you can't survey very easily. And we had to tell him, do not do this with Wi-Fi. That is not a good technology for this. But cellular could be, right? There's no Wi-Fi network out there. Right. He was like, oh, but if I just make a chain of them all the way from the ranch house out to the edge of the fence. And that is one of the kinds of things that led us to start thinking about cellular. So Particle is, I'm trying to think if this is worth drawing. I'll give it a shot. Particle is a cell carrier. When you buy a, let's see, in our Gen 3 hardware, so this one over here I'm showing you is an argon. So we have the argon is Wi-Fi. We have the boron, which is cellular, and we newly introduced the xenon, which is, oh geez, am I going to be able to draw this?
I don't know.
Let's see. Oh shoot, I screwed it up, but
it's approximately.
It's 3 hexagons, and then I messed up at the end. But that's sort of our symbol for mesh. It's an open thread mesh network. In case
that's fine.
Icon doesn't mean anything. And all of these devices also have Bluetooth on them. And so if you want to create a mesh network where the gateway is a boron, you have a cellular gateway. You buy a boron, it comes with a SIM card. Okay. Gotcha. Nice little SIM card that I can't draw.
That's impressive. Oh wait, is that the chip? The little chip?
Yeah.
Okay, good.
And you punch it out and you slide it into the device. Because just like if you go to any cell carrier, you get your phone, you get your SIM card, you put the SIM card in the phone. A SIM card is essentially the credentials that let you connect to the tower. So Particle is a cell carrier. So you get your Particle SIM, you have your Particle cellular plan, you can set the data limits, sort of a lot like Google Fi. You can just activate and deactivate SIMs for your IoT fleet of 10,000 things as you see fit. You can set data limits for the whole fleet or for the individual devices. But the kind of operator we are is called an MVNO. We are a mobile virtual network operator. We have that V in there because the folks like T-Mobile, AT&T, Verizon, Sprint, they are MNOs. They are mobile network operators.
I was going to ask if you had to cover the entire country with your cell towers, and I know the answer now. And that's great. I'm glad that you did not have to do that.
Speaking of things not to reinvent.
Right, exactly. So thank you for supporting that. We'll call that undifferentiated heavy lifting.
There you go.
Yeah.
So we have contractual arrangements with cell carriers to use their towers throughout the world. So we are a cell carrier globally.
Okay, cool.
And that's because we are an MVNO.
I wanted to go in the direction of power for a second because we've been talking a lot about, or it keeps coming up, limited resources.
Yeah.
I can get my mobile phone battery to last for about 3 hours on a good day. And then like you talked about, covering the fence at your ranch with a bunch of now mobile connected devices on your mobile network. If those lasted for 3 hours before you had to go recharge them, that would be bad.
Yes.
Is there just a really long extension cord? Like, what is the power consumption? Then you also mentioned earlier on the device, I can't remember if you called it device cloud or whatever, but
that is the word we use, device cloud. Sure.
Good. Using UDP and sort of more constrained protocols and all that kind of stuff. So just tell me a little bit about how you get mobile, which we all think of as, it is a very restricted environment, but we all think of it now as like, everyone on the BART is watching video.
Exactly.
Right? It's this huge band. We have this totally crazy concept of what mobile is, but this is really constrained, I'm sure, in what you're trying to do there. Yeah. So how do you manage power and how do you talk over mobile in a way that's very efficient for these devices?
These devices, they certainly don't play video, right? They don't even stay awake as often as our phones are. Our phones, like once you power it on, it is running, right? Many common use cases in IoT are, it's read a sensor, send the value, go to sleep for 2 hours.
Okay.
Right, and the sleep current on these things is something like 60 milliamps or even lower if you optimize that more. So they can last on a battery without a recharge for easily weeks, months if you do a little tweaking. At that point, you need to start adding a solar panel, bigger batteries, something, some way. Like if you're going to deploy it in some place where it cannot be recharged, then you need some kind of power generation. But you don't need much. Many of our use cases are either, you'd take one of these things and you would throw it on a truck, and I don't know. God, I'm bad at drawing.
That's actually pretty awesome.
But you would, you'd put some magical box right here that's cellular, and it's sending information about how maybe the fuel efficiency of the truck, maybe the temperature in here, or you might have certain pallets, you're shipping things in them that have to have certain temperatures or pressures. Maybe you're shipping tanks that have to know if they're full or know if they're leaking, and that might cause an alert that something is leaking. And you'll go through this ride, and you just need to make it the 5 days or something driving cross country, and then you can recharge it. And any time that we're working with a customer, it's important to us to help them develop to operationalize the business of how they're going to run this IoT product, because our customers are often coming at this from, we are a company who makes widgets. We make boxes that get shipped in trucks. Mm-hmm. We don't have any software engineers. We don't have any data scientists. Yeah. But we hear that IoT is a hot thing, and all the analysts are telling me that if I don't get into it, I'm going to lose my market position to my competitors and all these things. Right. So, I have helped our biggest customers interview engineers, actually, because they don't have any and they need someone to run their IoT initiatives.
That's an extended service.
For
sure.
Full service, turnkey, white glove.
Yeah, exactly. Yeah. Wow. That's very cool to think about. So I certainly think as the engineer in me that's excited about sort of IoT and embedded devices and stuff is thinking about how do I just build the application and already start thinking about, but then how would I tune it for power consumption, and then how does it live in the world? Like, how does that device move around and get charged and be protected against the elements and still have...
When something goes wrong and you need to send the technician out to the thing, how do you get diagnostics off of it? We try to provide as much automated remote information as possible, but sometimes the things they go offline, right? And you've got to roll a truck out to it, and companies have to plan for it in their operating model.
Got it. And is it, I don't really know how to ask this question effectively, but is it the kind of thing that's almost a commodity where, you have a fleet of trucks with these things attached to them and you'd say, yeah, that one broke and we're just going to give you another one and then we'll send that one back? Or are they sort of precious enough to many of your customers that you would go out and fix them?
There is a spectrum. It depends. So let's talk about micromobility. This is honestly one of Particle's best use cases right now. We get so many inbound calls about this. So let's say that you want to start a micromobility company. This is a connected pogo stick company.
Just for example.
Just for example.
I think it needs handles.
Yeah, here, I'm gonna make it kind of church key like there. Nice. Innovative design. And so these things, they'll have some little box on the side that is connected over, not Wi-Fi, cellular. Got to make our icons specific here. So the pogo stick is locked. They say the spring is all pushed in, whatever. Not an effective pogo stick. You come up to it and scan it with your phone, pew, pew, and you're a user of this, myawesomepogoservice.com, and you sign up with your username. This mobile app for My Awesome Pogo Service would use the Particle SDKs for making their iOS and Android apps. So they would, it is white labeled, like you don't see Particle's name on it anywhere, but they're using our libraries to, for in their code, it's one line of code like do the setup, and then we lead the user through a bunch of screens to pair with this thing, make sure that, whatever they need to do to interact with this device. They would often, the mobile app would be making a call to, let's call it Pogo Cloud, which would make a call out to the Particle Cloud, which would then talk to this device to unlock the pogo stick. And then you get on and you ride, and the app is showing you your time, and then you lock it up, and the message, whatever appropriate messages this thing might regularly be saying, here's where I am. It's me trying to make a map pin.
Got it. So like distance traveled or time spent.
And how much battery is there, right? You're gonna have to have some model for connected pogo stick company to have people round it up and charge the pogo sticks overnight. But they would be using our SDKs in their mobile app. They would be programmed. They would have written an application on Particle that runs on every single one of these boxes that has the controls to lock and unlock the pogo stick, to know where it is using GPS, to report where they are, to whatever alerts like somebody's trying to move me when I'm supposed to be locked up.
Right.
And that's all a matter of what this company wants to track in their cloud and on these devices, and what kind of sort of local, there might be a Bluetooth setup process, for the local before, like say you're in an area, the Pogo stick gets dropped in an area with low cell coverage. Very real use case. Yeah. You have to have some local way to talk to the device because you don't want somebody to walk up and like the app to say it's unlocked, but this you can't actually reach it because there's no cell service right there. Causes bad user experience, so you need some local communication as well.
One place we were headed earlier is we were talking about again the constraints, right? The limited capabilities of the hardware and the device, and we've talked a lot about communication back to your device cloud. What's unique about that compared to how all of us who are building web apps with pretty fat conversation, high levels of traffic? How do you sort of optimize for that environment?
Let's talk about protocols. Let's see. All right. So one reason that we had to, back on that first slide, make a device service, make a thing that is different from a REST API. You might just say like, why can't the devices just talk, HTTP over TLS the same way as my phone?
Right.
And heck, JSON, while we're at it, let's imagine you want to talk HTTP, the normal way that our phones talk, HTTP over TLS, JSON, JSON over HTTP over TLS, and just for giggles, we'll make clear the things we always assume, which is over TCP, which is over IP, which is over Ethernet, whatever, Imagine you want to do this in a very constrained environment. Just the JSON layer. Let's say, imagine you only had 10 bytes of memory. You got to remember that first opening bracket. And then you're like, okay, then there was a quote, and there were some letters, there was another quote. Did that match back up with here? Okay, yeah, it did. Okay, and then there was a colon, good, this is still parsing fine, and there's another. And you keep going and going and going, and it takes so much memory to remember all of this until you get all the way to something that matches back to that. You cannot parse JSON without that much memory. On these devices, we do not do that. So instead, we speak, and to be clear, this is something, sometimes this causes confusion for our customers. They're like, wait, but what if I want to use this protocol? It's like, use whatever protocol you want, it's fine. I'm talking about what we do under the hood where you don't need to look. So what Particle does, we use a protocol called COAP, which stands for Constrained Application Protocol. COAP goes over, let's see. Here we said HTTP. So COAP is, it's equivalent sort of both to JSON and HTTP in this other diagram, other list. The encryption it uses is DTLS, which is essentially the UDP version of TLS.
Okay.
D stands for datagram TLS. And on down, although, when you get to cellular, it's not necessarily Ethernet, but that gets abstracted from us. Thank you, dear cell carriers. COAP is specifically meant for constrained devices, thus the CO. So the smallest possible COAP messages is 4 bytes. It is a binary protocol. So if you think of HTTP, you've got a header name, colon, the value, carriage return,
Right,
header name,
right.
colon, and already there you've got this huge. You're using so many bytes compared with 4 for a very small CoAP message. The first 4 bytes of the CoAP message are there's like a couple of header bytes that are things like what version of CoAP are you using, and sort of a length field that matters for later. And then this is a message ID for a couple of bytes right there. And many CoAP, there's a status code that's built into some of these early bytes, and it's to get an idea of how constrained. We're trying to make use of every single byte here. So the status in CoAP is a constrained binary version of HTTP.
Okay.
Essentially, it takes all the great things that we learned about HTTP over the last couple decades and made it tiny and binary and parsable in very low memory. Status codes are a lot like in HTTP. You've got a 400, you've got a 203, a 205, whatever. And the way that you encode those statuses in 1 byte, where the first 3 bits are the, like, is it a 200 code or a 300 code or a 400 or 500? So that first number is the first 3 bits, and then the last 5 bits are the second 2 numbers of the status code. So they're trying to squeeze every single bit.
And they map specifically to HTTP codes, though, so they're using the same model?
Exactly.
Got it.
Yeah, it's like that has been refined over decades and works really well. You have, there are CoAP messages can be requests or responses. And for requests, they have a verb, right? So there is like, I don't remember right off the top of my head, but there's a couple bits essentially that are, is it, get, post, put, delete, etc. So a couple bits to specify that. You got 8 bits to specify the code. If you want to specify and responses can be, responses then have the status code, right? If you want to specify a path, you have what are called options. So you have extra bytes, and it's always the kind of encoding that CoAP is called, let's see, 3-letter acronym, TLV, type length value, right? So, so it's always of this structure where you first say, what am I talking about? How many more bytes do you need to read? And then read that many bytes, right? So if you want to add one element of it, let's say you are, in our device OS, you're publishing an event. You're saying, I'm reading the temperature and I'm publishing a temperature event. I'm saying the temperature is 60 degrees. And the way that we do that under the hood is with a CoAP message that's post /e, so E for event, slash whatever the, put a colon there, event name. So post E, and then whatever in your user app, say it's a temperature event. So let's say it's E /temp. If a device sends post /E /temp to our device service, that will get processed in various ways to send maybe a webhook out to your alerting system if that temperature is too high, right? So the way that CoAP encodes this is you would say, I'm going to add a URI path option. And the first byte will be, if I might be wrong about this, but I spent a lot of time here over the years.
I'm sure there's a spec that people could look at if they want to double check.
Exactly. It's an IETF RFC. So B1, because the first one, the first nibble, the first 4 bits says like which option are we talking about, and they come in a deterministic order. So this is how much do you add to the last option type you were looking at. B is 11 is the URI path option, and 1 means read 1 more byte. So that's the length, and then the value would be, the letter E here. So one URI path option gives you the /E. So with in this case, it was 2 bytes, which would be the same as if you just encoded this in ASCII. And then it's the same as writing out that next string for temp. So you'd have, 0, 4 means don't change anything about the type. It's still a URI path option, and read 4 more bytes, and that's TEMP. So and there might be some other things in the CoAP message, but in the end, you get a message that's something like 20 bytes that can always be parsed as you're parsing this bit. You only need 2 bytes of memory, and then you can reset, and you can use 4 bytes to.
And you can effectively operate on this and discard it to some degree, and then move on.
You can keep one little pointer, go through this this thing in memory in one pass, and keep on changing state and discarding it, and changing state and discarding it as you go through in one pass.
So in I'm super dating myself, early 2000s, I worked on a protocol called wireless binary XML.
Cool.
It had no XML in it.
It
was
was
basically
trying
like
something
this.
like this.
Right, exactly. Yeah. It was taking some other implementation that no one uses anymore of a particular protocol, and then compressing it down. This was only for mobile phones, but mobile phones weren't quite as good back then as they are now.
Totally. We often talk about IoT as the third revolution in computing, the third stage of computing, where you had PCs, and then it got computing power constrained, and the scale of deployment massively increased with mobile phones, and then with IoT, it's computing power scaled down,
same set
scale
of problems,
deployment huge.
New objective, but kind of the same set of problems. So one of the things that I remember from that was the frustration of being a software developer and debugging, for example, staring at streams of binary going by and knowing that one of the characters was wrong or one of the bytes was wrong, and then trying to figure out what I had done, and just sit just basic stuff, TCP dump, right? And so not strings, it's hex or whatever, and then sort of dumping that out. So how does that work for you? For the engineers that are working on this part of the infrastructure, do you have built up a set of tools that really help you to do that effectively?
I would say we have some, and we keep building more, because that continues to be a difficult problem. Especially, a lot of people have been talking about the distributed tracing, that kind of thing lately. As you build out a big set of microservices that all talk about these things, how do you debug when the device set some bits, and then it passed off to the device service, which changed some state in the database and passed along some of those bits, and it kept going to more and more systems. How do you trace that through? We keep having to build more tools. I drew a little cake here because back in 2013, when we were first building out this protocol, when we first released the Spark Core, my birthday came around in November, and people got me a birthday cake where they just told the person making the cake, they just gave them a string of hex and said, just trust it, just write this on the cake. And it was I might even be able to remember, it was an acknowledgement response of some 200 code. It was a successful change. I don't know if that's 205 or whatever changed is it was a successful, the message ID was 36, which is how old I was at the time. And the body, or maybe it was a URI path, was /bday. And I basically decoded it there on the spot, looking at the hex. And
I'm just trying to imagine the person in the bakery.
Right?
Where you're no, just take these letter by letter and just put it on the cake.
And
you don't need to understand.
It was in mid byte, it wasn't an even number of letters on each line. It was really funny. Anyway, I know that person had a weird job that day.
For sure. So building tools, but that's still a problem.
But absolutely.
I guess you abstracting that is what makes it great.
It's a problem for us, not for our users. We keep on, we have a tool called the console. So one of We'll back over here. If you go to console.particle.io, that is the main place that somebody comes to do fleet management. And it is a front-end interface to the API. This is where folks will see the health of their overall fleet, how much data they're using, diagnostics for one particular device.
Got it.
If devices are quarantined, like there is a device that's pretending, it says, I'm one of your products, and you haven't previously known about that device ID, and you're like, are you though? And sometimes that's really helpful because sometimes our customers forget to collect enough data on their manufacturing line, and then they're like, oh no, there are things out in the world that are going to connect, that should connect, that we didn't gather enough info. So often it's a signal, but then they can approve it in the console.
Got it.
Things where we try to make problems that come up in IoT just go away.
Go away for other people.
But there are a lot of diagnostics exposed in the console, which help with debugging.
That makes me think of two questions.
Yeah.
One, what do you think is the most interesting problem that you've had to solve in all of this? Like these are all interesting to me, but like what is the thing that really stands out as something that was really sort of challenging or interesting? And then the second question, which maybe we'll come back to because you'll forget while you're answering the first, is what are you excited about next? What's the most challenging thing coming up?
The most interesting problem has been challenging and interesting is everything here, because it's the thing that, for all this stuff, there are front-end frameworks that we can use. There's standard tooling for load balancers in front of this. There are lots of standard off-the-shelf things that we can pull.
Yep.
Everything over here, not so much. We, have to build a lot of this stuff up from scratch, and that has been interesting and difficult and really fun.
So actually, just on that point, I mean, as a founder and CTO, I assume that you spent a lot of time over here in the early days.
Yes, exactly.
And so,
in the early days.
So how has that evolved? I mean, how did you know something about this stuff when you started, or was it?
No.
I'm gonna download some specs and solve some problems because I'm excited about this space. And
yeah, basically, I was at the time like a Ruby developer who was making web apps for people. I had done some electrical engineering in college, but I was like, let's write firmware. Okay, dive in. I wrote the early versions of the firmware and the device service and wrote the spec for this protocol and revised it. And also, to be clear, CoAP was not finalized. The IETF spec was still in draft, but when we were looking around at that time, it was by far the best one. It specified things about security. It didn't leave a bunch of, and make the rest of that stuff up yourself, as protocols so often do. MQTT is one in this space that has a ton of traction, but the spec is very bare and it doesn't specify any security. So if you want it secure it yourself.
Which we do, by the way.
Yep.
We want security.
Yep. So there are lots of things here. We took it because it was the best thing that we saw out there at the time, but the spec wasn't even finished and has definitely evolved since we put our implementation into the device service and into hardware and ship that hardware to people.
Yes, there's one thing about embedding stuff, right? You're going to have it for a long time. So before I still let you even get back to my second question, the other thing I'm interested in from a sort of founder, CTO perspective is now you're a larger organization, you have a lot of customers.
I don't write any code anymore.
Right. So this is a very much a CTO to CTO question. Have you been through that feeling where you bring people in and you see them do something that you did so much better than you could have ever done it, and it's like the most joyful thing?
Oh yeah, where they do it better than I could have.
Right,
yes.
exactly. Yeah. Where you're just like, oh man, this is fun. It's fun to see people who really, like, it was fun to get it off the ground. That's stage one. Like I'm a Ruby guy and I just like figured out how to do some stuff because that's cool.
Set up my
But now I'm watching some people really do this well, and that's like
who actually know what they're doing, have been doing it for a long time, have incredible architectural minds, who have to scale up the systems that worked for us when we had 1,000 customers and then 10,000 customers and then 100,000 customers, and they now they have to keep on scaling things up, and there's always that feeling of like, oh, you want to hold on, it's better just let them go, and it's awesome to see what they do with it. And I've got an absolutely amazing team of folks.
That's awesome. So then the future, like what's kind of the next big, whether it's architectural or technical or even just in terms of the business as you grow, like what are you excited about that's going to really move Particle forward?
As of, let's say, a month ago, particles, this is a thing we can draw. People! So these, like you say, CTO to CTO conversations. This is, sometimes we talk about tech things.
Right, now we're drawing org charts.
Now we talk about how to run an organization effectively. So how Particle did work as of a month ago, we had a whole bunch of people, and they each had a list of skills, and essentially we would have, here's an initiative, and we need one of this and one of this and one of this. Mm-hmm. And so from the entire pool of engineers, we'd say, okay, we would have ephemeral squads.
Got it.
We'd pull from all the engineers, folks to create this squad, and that squad would meet daily, stay together, manage their project together for a couple months or however long the initiative took, and then it'd be done, and they'd go back into the pool for to work on the next initiative that came down the pike. Mm-hmm. Now we have just changed, and everyone is very excited about this new model, to where there is much clearer product ownership, where you have these let's call it 3 people who have these 6 areas that they own. They own let's say device communications.
Right. Okay.
Which is that whole the device OS and the device service and the protocols in between. Yep. And you'd have another group of folks that have the hardware designs and the device OS release schedule and things like that.
So really breaking the overall system up on domains effectively, and then assigning teams to those and having people consistently work on those.
That's our embedded platform team. And then you've got, and we took the folks we have now, broke them up into 7 teams with clear product area ownership. Mm-hmm. And as we grow, many of those teams will grow and then split by mitosis into other groups that are more. Maybe these lists are too long right now, and eventually, when we have enough people, they will split out. So that was a great change, and there's lots of really exciting talk right now. We're setting our Q3 OKRs and making a Q3 release plan right now, and everybody's pretty fired up.
Great. Well, thank you so much for taking the time to come in and chat with me. I learned a ton. Everything from binary protocols to organizing people. I think we've covered the CTO role at this point. But tons of new information for me. Not really the space that I spend all my time in. So this has been really helpful. Thank you so much for coming.
You are very welcome. I had a blast. Thanks for having me.